Hi there. So right now what we're going to do is talk about section 2.2, which is the derivative function. Okay, in this section we are going to not only look at the derivative of a function at a point, but we want to consider the derivative of the function for all points in which it's defined. Okay, and it turns out that the derivative of a function is actually a function itself. Now, why should that be true? Well, if you think about it, remember the derivative of a function at a point, let me draw a graph here. The derivative of a function at a point is precisely the slope of the tangent line at the point. Now, we can find the slope of the tangent line for absolutely every point for which it's defined. And therefore, remember, in order to be a function, each input has to go to exactly one output. And I think you'll grant me for every single point on our function, there's only one slope of a tangent line that exists. Okay? So we know that the derivative of a function is a function itself. And what we want to do is kind of play around with graphing these functions and then also looking at what the graph of the derivative is, because what we're going to do is see that there's some relationships between these two. So let's start out with as follows. Suppose I have, and we're going to build, as always, suppose I've got a straight line. And my straight line goes through the ordered pair 0, 2, and say 1, 0. Okay? So this is my function, and what I'm going to do now is graph his derivative. Okay? Well, let's talk about this. I think that you'll grant me no matter where I am on this function, the slope of the tangent line is actually the slope of the line itself. It's constant. So technically, we can say, well, the slope of this line is -2, change in y values over change in x values. Hence, my derivative is the constant function y equals -2. Okay? Or I'll say y prime just for clarifications. Now, something else I want to note. I think you'll grant me that since this is a line, y equals mx plus b, the degree here of my function is 1. Okay? Now, what's the degree of a constant function? I claim the degree of a constant function is 0. Why? Because essentially, if the equation of this line is -2, we can write this as -2 times x to the 0. Now, at this point, you might be wondering why I'm talking about the degrees. Just hold on a second. Okay? All right, so now let's go with another function. Now let's suppose we have a nice quadratic function. We'll call this g of x. And let's graph the derivative in the next graph. Okay, so what do we have here? Let's talk about this. Notice, this is a point where my graph is changing from increasing to decreasing. Okay? So, I think you'll grant me that no matter where I am on this graph at this point, my slopes of my tangent lines are all positive. And they start out really positive, and then they get closer and closer and closer to 0. Okay? So, my slopes are very positive, and then as I get closer and closer and closer to my vertex, they're getting closer and closer to 0. What does it mean for my slopes to be really positive? It means that my slopes are really positive. Excuse me, let me draw that a little better. My slopes are really positive until they get to 0. Now, why did I draw this as a straight line? Because since this is a quadratic, what we're looking at with the slopes, they're changing essentially at a constant rate. Now, right here, my slopes are 0. That corresponds to this point right here. And then what happens? Well, they start out at 0, and then they get more and more negative. And remember, more and more negative means below the x-axis. Now, why is this a straight line? Well, because we know with a parabola, if it's drawn decently, that one side is a mirror image of the other side. So whatever rate things are happening at on one side is equivalent to the other side, just in the other direction. Okay, well, we know that the degree of quadratics are 2, and we know that the degree of straight lines are 1. Okay, let's take another graph. Suppose now I want to take a graph like this. We'll call this h of x. And then over here we'll graph h prime of x. All right, so what do we see here? Well, let's talk about this. I claim that these are pretty darn significant points right here. The reason being is notice that my graph is changing right here from increasing to decreasing. And over here in a similar manner, my graph is changing from decreasing to increasing. Okay? What's happening right here? What's the slope of my tangent line? I claim at both points where it's changing from increasing to decreasing or vice versa, my slopes are 0. Okay, remember over here we're graphing our slopes. Our slopes are 0. All right, now another thing, look here. My slopes of my tangent lines are really positive. What does it mean to be really positive? It means really up here. And then they're approaching 0 as I get closer to this point. So they're really positive. Then I'm approaching 0. Now between these 2 points, what's happening? Well, my slopes are 0 here, and they're getting more and more negative, and then they are approaching 0 again. So they start out at 0, they're getting more and more negative, and then they're heading back to 0. And now to the right of this interval, what's happening? Well, we're starting at 0. And then as our x values increase, notice my function values are getting bigger and bigger. All right, well, we can look at this as a cubic function. We can say this is degree 3. And I think you'll grant me what we have here looks very, very much like a parabola, which is a second degree function. Okay? Let's do one more. I've got room for one more up and down here. So now we'll call this k of x. And suppose now my function looks like this. Okay? And I will put k prime of x right down here. Now again, the first place that I always hone in on is as follows. Wherever it's changing from increasing to decreasing or vice versa. Notice that's changing here, here, as well as right here. And at each of these points, if I was to estimate the slope of my tangent line, it sure looks like it would be at 0. So, try to estimate those guys over here. At those 3 values, the slopes are 0. Now, what's happening to my function over here? Whoa, my slopes are really negative. They're really negative. And as I'm getting closer and closer to this point, they're getting less and less negative until I get to 0. Really negative until I get to 0. Now, between these 2 points here, well, my slopes start at 0. They're getting a bit bigger until they go back to 0. They're getting a bit bigger until I go back to 0. In a similar manner, between these 2 values, what's happening? It starts at 0, they're getting a little bit negative, and then they're going back to 0. Starts at 0, getting a little negative, goes back to 0, and then notice that they're getting super positive. Okay? We know that this is an even degree function, again, because both arms are up or both arms are down. In this case, both arms are up. So what I can say is, for simplicity, let's say this is a degree 4 function. Well, what's the degree of this guy? Remember, when you have an odd degree, one arm is up and one arm is down, either this way or this way. So for simplicity purposes, we could say that this is degree 3. So what I would like to do now is look at patterns. Mathematics, as you guys know, is all about finding patterns. First off, notice one thing. The degrees keep decreasing by 1. Okay? This is not a fluke, and you'll actually see why this is the case once we start computing derivatives. Something important to notice, though. The other thing that I want you to notice is as follows. Wherever my graph seems to be changing from increasing to decreasing or decreasing to increasing, so right here, and over here, notice the derivative is 0. The other thing that I want to point out is wherever my functions are increasing, my derivative is positive. Wherever my functions are decreasing, my derivatives are negative. My function is increasing here and here. Notice it's positive here and here, above the x-axis. And in between these two guys, my function is decreasing and my derivative is negative. Remember, negative is below our x-axis. So what I want to do is I want to write down these patterns because they're extremely important to note. And they're definitely something that you should have available to you until you start to get more familiar with this material. Okay? When f of x is increasing, that happens if and only if the derivative in that region is positive. Your function decreasing happens if and only if your derivative, your slopes of your tangent lines, are negative. And, well, if f of x is constant, then we know that the derivative is 0 in that entire region. But we can also note that at a particular point, the derivative is 0, where your function is changing from increasing to decreasing or vice versa. Okay? So, when you have a graph of a function, we've seen that you can graph the derivative by using this idea. Now we can also go the other way. Okay? So, going the other way, what do I mean by that? Well, suppose I give you characteristics about the derivative, and I want you to sketch a possible graph of the function. Well, let's do that. So let's draw a graph of a continuous function, and we'll formally define what it means for a function to be continuous, but at this point let's just think about it in a crude manner in the sense of it means you can draw your graph without lifting up your pen or pencil. Not a mathematically precise definition, but this is fine for right now. We'll call this function g of x, where the derivative is equal to 0 when x is less than 0. The derivative is positive when x is between 0 and 2. The derivative is negative for x greater than 2. And then I'm also going to say that the derivative is equal to 0 at the point 2. Okay? Now, when I do this, what I'm saying is we're going to sketch a possible graph. Why am I saying a possible graph? Well, precisely because there's actually infinitely many graphs that we can draw that satisfy these characteristics. Okay? So, let's just go through right now and kind of make our associations here. My derivative is 0 on a whole interval. So when x is less than 0, all over here, my derivative is equal to 0. Well, that means we've got a constant function, okay? Now, I could draw my constant function up here. I could draw my constant function down here. That's why there's infinitely many sorts of functions we could draw that satisfy these. All right, so it's constant when I'm less than 0. Now, what happens between 0 and 2? Well, my derivative is positive. What does it mean for my derivative to be positive? That tells me that my function is increasing. So now my function starts increasing, and notice that 2, right at that point, my derivative is 0. That's where it's going to be changing, because notice for x greater than 2, my derivative is negative. In other words, my function is decreasing. So this is one such graph that we could draw of this function. Okay? Now, we can do another graph too, just so that we get a little bit more practice. Now again, let's draw a graph of a continuous function, and let's have it be satisfying this. My derivative is positive when x is between 1 and 3. My derivative is negative when x is less than 1 and when x is greater than 3. And my derivative is 0 at 1 and at 3. All right, so what does this tell us? Other than the fact that 1 and 3 are pretty darn significant values. What this tells us is that when we're between 1 and 3, my function is increasing. So between 1 and 3, my function is getting bigger. Notice when I'm smaller than 1, I have a decreasing function. And that same thing happens when I'm greater than 3. And what this says, when your derivative is equal to 0 at a point, it means that that's where we're changing from increasing to decreasing. So what do we have? I always like starting on my left. So when x is less than 1, I've got a decreasing function. Okay, I know it changes from increasing to decreasing from 1 to 3. And then it goes back into a decreasing function. All right, I hope this was helpful for you. Thank you.